All right. Hope we're all doing all right today. I hope that we are making progress on the homework. It's good to have you all today. Homework is due tomorrow at 5. Had a couple people come to office hours with some good questions. I think in general, people have found that those questions are that the office hours are helpful. I think getting people going. All right. Don't disturb. All right. So but there should be another set of office hours tomorrow with both of the TAs to work things out. So hopefully everyone's making good progress on that assignment. Okay, so with that in mind, we're going to continue where we left off with the backpropagation. So the backpropagation part of the course is the next phase of this. Okay. All right. Sorry, people are trying to call me apparently. I don't know, that's rare. So no call ID. So anyway, so when it comes to so today's lecture, sorry, a little discombobulated. Forgot to turn on do not disturb mode, and every device in a 10-foot radius started buzzing. That's weird. Anyway, make sure we're good. Okay. All right. So with that, we're going to continue our backpropagation assignment. So I know last time we were sort of hacking through doing the backpropagation math. All right. So we're going to continue that, but then we're going to clean it up and then make it a bit more general. So right now, you might recall, so here's our backpropagation assignment. We were trying to do backpropagation through this very simple neural network, okay, where it's just an input going into a neuron with an activation function here, another neuron with an activation function here, etc., etc. Oh, and by the way, one thing I want to pull up here, a lot of people are not aware of this. I'm jumping all over the place. I apologize. This is for the homework, okay? So I'm going to pull up here. This here's the Canvas page. All right. On the Canvas page, if you're looking for help with the homework, there's this big link right here. This homework FAQ. Okay? Click there. And right on that, you can see that frequently asked questions that we have that come by that people come by the office hours with. Check here first. This might save you some time. Okay, it's really helpful. It's continually updated. When we have new questions, we try to put new answers on here. So that's a good resource for you. I forgot to mention that. So with that, let's go back to here. All right. And we'll go back to our notes. So we have here our very simple neural network, feed forward neural network, all these nodes, and we started putting together the backpropagation algorithm. Okay, the backpropagation algorithm we have in our notes right here. We had already done forward propagation. And now I want to do backward propagation. Now we had coded up the backward propagation right here. Okay, and I'll pull up the code. This is where we were in the code. I hear you. And you're one step ahead of me. If you're in the Zoom, there's a link to the viewable link. Okay? All right. Any other questions before we get started? Yeah. The TA office hours, if there's any confusion about office hours, I believe it's noon tomorrow, but it's on the Canvas page. All the office hours are listed there for the entire for myself and the TAs. You got it. If there's ever any update on the office hours, they're always listed there as well. If there is a sudden change in office hours, we will announce it. Okay. Other questions? Let's just do a little, all right, then we'll do a little bit of a review here. Here we go. TA office hours, 12 to 2 on Friday. The 2 hours of office hours tomorrow. So, all right. So we've got our forward propagation algorithm where we are looping through this loop right here. And that's what we see in the code right here, the forward propagation. We are taking our weights and our biases and the output of a previous layer, and we shove it through an activation. Okay? Then we continue. Then we take the result of that activation, shove it through the next activation layer, and voila, that's how we do our neural network. So the input goes there, goes into that function there, goes in that function there, goes in that function there. That's what you're seeing here. But the only thing is it's not written in too much of a loop right now, okay? Right now it's just, we're doing for the, this is just a plotting loop right here. Plotting loop. But we had manually said, hey, let's go from layer 1 to layer 2. Okay. Is there a way to loop it instead where you, if you have an arbitrary number of layers, you go from 1 to next, 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 next? Yes, there is. Okay. We almost did that last time, but I made a little bit of a screw up, but we can fix that this time if we get there. Okay. So the first thing you do is a forward pass of your neural network, and that tells you the value of the neural network. That the input, what's the output? That's the forward pass. And then you do the back pass, the back propagation, and that gets you the gradient. Okay. And that's what we have here. This code right here, the back propagation. We have already stored from the forward propagation the outputs of these H values from the previous, from the forward propagation step. And we use the back propagate backwards. All right. And we store the gradient of our base, of our biases and our weights. Okay. That's the algorithm right here. So right now we have just one forward pass, one back pass written up here. Now let's see if it actually works. Okay. So what we want to be able to do is take this gradient. And why do we need the gradient? Because we want to do gradient descent. We want to make this neural net fit this curve. Okay, this is a curve that the neural net we know the neural net can absolutely fit because it's actually made up of the same activation functions, the tan H's, the hyperbolic tangents. All right. So in order to do gradient descent, we have to start giving it data points, just like you're doing for your homework, and then trying to regress the mean squared error. Okay. So if we look at here, our loss function is MSE, the mean squared error, like we've done for all of our examples thus far that are fitting functions. Okay. So we've done a forward propagation. We've done a backward propagation. Now we have to do a gradient descent loop because the back propagation, that gets us the gradient. Forward propagation gives us the value, the output of the network. Okay. We have this 2-layer neural network we had set up previously. This is our notes from last time. Okay. All right. So now we need a gradient descent loop. So let's go back to our code. Let's make a gradient descent loop. Code. Let's make a gradient descent loop. Now, as you're all doing in your homework here, you have a gradient descent, which means that you need to have a step size. Okay. And we'll have the step size, we'll call it alpha, equals 0.01. I'm just guessing at a step size right now, and we'll see what happens. Okay. And then we're going to create a, then we need a tolerance to stop the gradient descent step. Make it 0.001. So this will stop the gradient descent when we're near the bottom. Of the cost curve. Okay. All right. And the idea is that this will fit okay. Now, where are we on our code? Just scrolling back here. We already have a loss gradient. We already have an activation derivative. Nifty. Great. Cool. So we're doing a gradient descent step. That means that we need to know the size of our decision vector. how many decisions do we have here? Okay. Well, our decisions, they are the weights and biases for each layer of the network. Okay. Keeping in mind that our network is very simple. Each of one of these little arrows here, okay, at least these two here. Let's see, what do we have here? We have W list 0, W list 1. Yep. Okay. Is going to have a weight and a bias. We only have one arrow going in. We don't have multiple of these activation nodes. We don't have multiple. So we don't have to worry about combinations of weights going across. We're going to have a weight and a bias. Weight and a bias. And so we need to have an initial weight and a bias. Where we go? The way we've defined it up here in our code. Here we have a B list. That was our list of biases, okay? And our W list, that's our list of weights. And where do we define those to begin with? Okay. All right. Oh, and this is a list of, and right now here, what we're gonna do is we're gonna change this, because right now, this is a trick of Python. So you see here, it looks like we made some kind of list, right? But that's not a NumPy array, right? The NumPy array we would get by making np.array and making a list there, okay? This specific type of list with the parentheses is called a tuple, a T-U-P-L-E, a tuple, all right? You want to be careful when using tuples. Apologies for doing that this way last time. Once you make a tuple like this, you can't change it. Well, we would like to change it now. Before we were like saying, oh, we have this list of just a 1 and a 2. That's fine. But we're going to want to update what these weights and biases are with the gradient descent loop. So let's turn it into a NumPy array, np.array. So np.array, and we want it to have square bracket, square bracket. Now it's just an array with 2 weights, okay? What weights are those? It's the weight for there, it's the weight for there, okay? And then there's a bias, which just adds a number to the input of that function. So keeping in mind, this is a reminder, the number that goes into this activation function, right, is going to be some weight, some weight times the input plus some bias, right? And if it's the first weight and first bias, there it is, right? Weight is multiplied by the input, bias is added. And over here would be weight 2, x plus b2. There's our weight and there's our bias. A little bigger for you. Sorry about that. Apologies. Yep. Yep. There we go. So back to the code. So we're going to change this to a NumPy array, and we'll change this to a NumPy array. The reason is that these tuples, which are just the little circle braces per parentheses, they are immutable, meaning that you can't change them once you make them. And that's bad because we want to change them. All right. So we made that, and I don't think that'll change anything. If we hit run all, hopefully it won't create any issues. Y hat is not defined. I think I have a Y hat. Okay, I think we had to define Y hat somewhere. But I don't think we need this loss function right here. I'm going to get rid of this at the moment. If that's throwing an error, we don't need that at the moment. Good. Okay, everything runs just fine. There was something throwing an error. That was just for illustrative purposes last time. We're going to get rid of that little piece of code. Okay, so we have a gradient descent loop. Now we want to be able to update our biases. Well, we had that W list and that B list, right? So that's the W list and the B list. Okay. And so we're going to make this a loop that doesn't stop until the gradient is small enough and it's hit the bottom, okay? So we're going to say done equals 0. And we say while done equals 0, the double equal sign is a comparator, comparing it to 0. We do our gradient descent loop. This is our gradient descent loop. Okay. And now we are now indented. Keep in mind we have that colon, so we're now indented. Everything indented is now inside the loop. Okay, so now we need to do our steps for our gradient descent. So a reminder for our steps for gradient descent. So reminder, gradient descent. Steps. First thing you got to do is you start with an initial guess. Of your decision vector. Okay. Now our decisions here, we have we have a lot of different decisions. Well, not a lot. We have like 4, but we have all of our weights. In this case, we have our weights and our biases. Okay. We already have an initial guess of a decision vector. We've set it way up higher in the code where we said that W list is equal to 0, 0 or whatever, right? Or 1, 1 and 2, 2, right? We've already done that. Okay. Okay. So now 2, we want to make sure that, so then we can check the value and gradient of the cost function. And our cost function, we know this time, we said it at the beginning, is the mean squared error. We want those curves to be similar. The mean squared error makes those curves similar, okay, of the cost function. Okay. Okay. Right. Right. We want to check the question. Nope. Okay. So let's say, just for the sake of argument, we're going to call our decision vector, we'll call it W. That might be a little confusing because the weights are also W, but in general, our decisions we'll call W here, okay? So the value of W, so the value of the cost function will be f of W, and the gradient is lowercase upside down triangle f of W. Okay, that's the gradient. So, and the gradient descent, we say, hey, our update of our decision vector is equal to our previous one, okay, minus alpha times the gradient evaluated at W, okay? Written in a few different ways, this is basically, it's the same thing, okay? We find the gradient, we descend the gradient a bit, and store it, right? So we have to do that here. It's just computing the gradient is a bit more complicated. Computing the value of f is also a bit more complicated. You'll notice that, oh, and of course, it's like, so if the norm of the gradient is greater than a threshold that we set, then go to 2. Okay, that's the gradient descent loop. All right, so we are looping on the gradient descent. Okay. All right, so we are on step number 2. We've already done our initial, we've already assigned our initial guess. We put that way up higher in the code. That's what the B list. So we're going to use, we will update B list and W list in the gradient descent loop. Okay. So we're going to check the value of the gradient, the value and gradient of the cost function. Okay, we have a way of checking the value of the cost function. Right now, it's just this list of code right here, right? Look at this. So so right now so it's all this code in the forward propagation, right? So where we start with some h list is equal to something is equal to x plot. Okay, it's some current input. Okay, then we do an activation h list. So given the fact that we're going to call this over and over again, let's turn this into a function. Okay, so let's make a new function. Okay, so we'll make a new block of code, make a new function. We'll say we're going to create a forward propagation function. Okay, so that way we can just call it. So define forward prop, we'll call it. Okay, and what do we want to send into this function? What do we need to send in? We got to send in our, well, let's look at our neural net, right? We look at our input, that's what that x is, and we need to know what our weights and biases are. Okay, so let's create our weights and biases. So we'll call our input x, that's our input, our w list, and our b list. Okay, now let's see what happens. So we can do forward propagation, and now we do a colon. So now basically what we're going to do is we're going to copy everything that we did in the forward propagation code and put it inside of that function. Where is it? Where is our forward prop? There it is right there. Forward propagation. All right. So we need a couple things. We need y hat plot. Okay, no, we don't need that. So we're going to say HList0 is equal to our inputs. So recalling that this here, right, that's H0. Covered this before. Okay, so H0, we'll call it H0, is just equal to your input X. Okay, all right. So I'm going to copy this. I'm actually going to copy just all of this, friends. Okay, copy this. I'm going to change it. See that? I'm copying. I'm going to scroll it down into my forward propagation function. Okay. So I'm going to clean this up a little bit. I'm going to say that H0 here is equal to X. Okay. That's this right here. H0 is equal to X. And then it's going to be multiplied by W1 and added to B, and it's going to be activated. So H0, we'll call this, let's clean everything up here. We got B list, H list. Okay. We're just cleaning up the language. So we're going to say this is now H0. Okay. And then we're going to call this H1. We're going to call this H1. Okay. And this will get us the prediction. So H, this is the prediction. It's the output of the neural network. Okay. But at the very end, what we want to know is the cost. So what is the, it's going to compute. So we can compute the cost, but so we'll get the output. We'll call it y hat. So what we'll do is we'll return y hat. I don't like the plot thing. I'm gonna get rid of this thing that says plot. Let's get rid of plot here. And for your own edification, for your own help, I'm just gonna take this code and just copy it once we're sure it's working here. Okay. And I'm going to copy it into the Zoom window so that way you can see what the small changes were. Okay, there they are in the Zoom window. All right. Do we want the? No, we don't want the. Was it the y hat I? No, we do not want the y hat I. I is gone as well. Thank you. I'll put that in there. So close. Thanks, friends. Yeah, we're cleaning up our notation from last time as we clean up our code. Thank you very much. All right, so I'll just put this in again in the chat window. Also, you can follow along at the link. Okay, I believe the changes that are being made. So we're returning y hat. This is the forward propagation function. So what does it do? It takes in weights, biases, an input, and returns the output of the neural net. What it does. Cool. Right now we have this sort of copy and pasted activation 1, activation 2. We can get rid of that later to make it even cleaner. But this works for now. Okay. So that's pretty good. But I will say it doesn't have, it's not giving us everything we're going to want yet, but we'll just one step at a time here, friends. Okay. So what we're going to need to do is store each of these H0s, because we need these for H0, H1, H2. We need to remember those for them when we propagate backward. So it won't be enough to just return y hat, the prediction. We're also going to have to return these H's. Okay? So we do H0, H1, and H2. Should be able to return all those things. Okay, let's see if this works without putting it in the gradient descent loop, just really quick, okay? If this works as we expect, then we should be able to return y hat, H0, H1, H2 are equal to forward prop. We send in our input, which just send in some X, which just say it's 0. Okay, we have our W list, our B list. Anything else? That's it. So if that's the case, this should run all right. Okay, well, it didn't error. That's a good thing, right? Let's print out y hat. Okay, didn't throw an error at the very least, right? But the other thing that's good is that it remembers H0. It remembers H1. We have it stored. And H2. Awesome. Great. Because we will need H0, H1, H2 for what? The backpropagation. So let's go up to the backpropagation. So let's scroll up to there. Okay. And we're going to put this all inside the while loop. So let's see. Okay. So this little line of code, we're going to indent and put this inside the while loop so it'll get looped like everything else. Okay. So there you go. That is their step 1 of the backpropagation. We want, or step 2, I guess. Here we got check the value and the gradient of the cost. Well, let's get the cost in there, which means let's make another function that's going to backpropagate through this simple network. Okay. Code. We're going to create a backpropagation function. Define. We'll call it backward prop. Okay. And in case you hadn't seen this syntax, this writing before, this just makes it so we return multiple things. And so whenever we call that function, we make sure we catch all these multiple things in some variables, right? So we can use them again, right? So, excuse me. So with that, we got to return. Okay, so we need to do a backward prop. And what does it need to take in? Okay, what are the input arguments? Okay, well, the good news is, so let's go through our code up above. We can follow that. Here we go. We need to know what the prediction is. We also need to know what the Y data was that we're comparing to. Okay, so we need the loss gradient. We need all this. Okay, this is all stuff that we can do. So what we're going to do is we are going to copy this backpropagation code, everything down to this G. Okay. So I copied all that, put a little colon there so we have an indentation, and then I pasted. Keep in mind, I would like all this stuff here to be indented so that way it's all inside of the function. If it's not all indented, it's not all inside the function. Okay. and we're just going to update we're going to update the variable names here so they're a little bit cleaner. Okay. And all your input is welcome when I miss a thing. It's entirely possible. All right. So what does it need to take in? Well, we're going to need to know our y hat, our prediction, right? Right. We need to know our y data. Okay. So we need to know our y data. This is the data that we're using to say, hey, this is our prediction. That's what our data point is. How different are they going to be, right? We need to know that for the cost function and also the gradient of the cost function. Okay. We're also going to need to know, A1 and A2, not the H1 and H2. I apologize. We need to know A1, A2, H1, and A2 and H2. So we also need to know what A1 and A2 are. When do we get those? We got those from the forward propagation. So that means in the forward propagation, we also have to return A1 and A2. My goodness. We can do that though. That's not hard. We just add it here. We said, hey, we want A1 and A2. Not bad. And then when we use this function, we want to make sure that we catch A1 and A2. It's the output of a function, just like we learned functions whenever we learned programming. Hey, catch A1 and A2. Again, cleaner ways to do this, but this is our first sort of hacky way of getting it done. So back to our backprop function. All right, so we need to send in H0, H1, H2, A1, and A2, if that's correct here. Now, we did change the names of our H's. It's no longer H list. We'll get back to that later. I wanted to make a nice list. Well, maybe today. We'll make a nice list later. Okay. It's just called H1. All right. Any other versions of H1? Here's H0. Okay. Is there anything else that we need to change? And then, okay. So that is the backpropagation. Y data. We don't need to make these values anymore. We are being sent those in, so we can delete those two lines. Okay. Computes the loss gradient, the activation derivative, which is H2. All right, and we have to send back. What does backpropagation calculate? What's the whole point of backpropagation? Is that it calculates our gradients. So we got to have this function of backpropagation return our gradients. So we need to return these gradients, and here they are. Here's the gradients of our first set of weights. Here's the gradient of our first bias. Here's the gradient of our second weight. Here's the gradient of our second bias. So let me just copy. So we want to return grad W1, gradient of B1. I'm just copying and pasting. Double click, copy, and paste. Again, there are cleaner, more linear algebra focused ways of doing this, which maybe we'll get to today. But there we go. It returns the gradient. So back to our, let's leave that up for a moment. So when we go back to our gradient descent, we want to make sure that we call this backpropagation function, and then we say gradient W1, gradient B1, gradient W2, gradient B2, they all equal the result of this backpropagation function. Okay. So then we plug this, let me just copy all this as it currently exists into the Zoom link in case you want to compare here. Okay, so I'm going to copy this and say I want all this to be equal to our backpropagation function. So let's go down below. All right, tab to make sure we're inside of our gradient descent loop. Okay, all that is equal to backward prop. And what were our input arguments? Well, it helpfully is telling us, right? We got to send in y hat, which we have not defined yet, but we'll just put it here. We'll call y hat. Okay. Y data. Okay. H0, H1, H2, A1, and A2 underscore 2. Okay. So this is the forward propagation step. This is our backward propagation step. Okay. And on our code, in our steps up here, that's this step, right? Check the value of n gradient of our cost function. Okay, well, actually, we don't have the cost currently. Do we need that? So I guess we don't technically need the cost here. We don't even technically need to do the forward propagation step to get the y-hat value, but we need all this stuff. That's what we need. Okay. All right. So that's step 2. Now step 3. Let's take a gradient descent step. Okay. So we're going to do this with just a point here. Okay, so we got W. So all of our decision variables, which are what, H list and B list. Okay. So W list and B list, we got to update these by saying it's the previous value that we had minus our step size alpha times our gradient. We've just computed the gradient. It's coming back of, the gradient of our first weight is grad W1. So what we can say is that our first weight, which we would say is index 0, okay, is equal to the previous value of that weight minus alpha times the gradient of that weight, which is grad W1. Okay, that's what we called it. Okay. And we can do this for all of our decision variables. Okay, we do that for our second weight, right? We just copy this. So our second weight, which is the second one in the list, index 1, because Python counts at 0 to begin with, W list 1, and alpha W2. And then we have a bias as well. So it says 0, our bias list 0, it's equal to B list 0, the previous value. Then we're going to do a gradient descent step, minus alpha times the gradient of B1, B underscore 1. And then we can copy that, 1, 1, B2. Okay. We took the gradient descent step. And then we say, hey, if the norm of the gradient is small enough, we'll stop. Okay? We can do that. What we're going to start with for now is we're just going to have it run through just a couple of iterations, just to see what happens to the values of W list and B list. Okay. So what we're going to do is we're going to print W list. And we're just going to print out the W list and see what happens. And then we'll say we will stop after n loop, a number of loops. So what we're going to do is we're going to create an iteration counter. And then if the iteration counter gets too high, we will stop and say, hey, we're done. We're not done, then we're done. So if we say iter equals 0. And then we can say, hey, if iter is greater than 5, iter is equal to iter plus 1, we iterate, else, we say done equals 1. Sorry. If it's less than 5, we add 1, and then otherwise we're done. Okay. All right. We're almost there. We can't run it just yet because we have not defined y hat. Okay. Because we haven't defined y data. This is the data point that we're going to use. We're going to grab a data point from this curve that we've generated. Okay, we're grabbing data points and then we are trying to fit. Okay, in our homework, I just gave you a whole bunch of data points, right? and you're going to try to fit the curve. You have a curve fit that's trying to hit those data points. That's what we've done in all of the past year. So I just need to come up with some data points we want to fit. I'm just going to start grabbing them, I guess. Let's just make up some data points here. What can we do? What can we do? Here's what we'll do. We will just say that y data. Let's just say that y data. We're going to grab that from, I'm going to scroll up. I'll scroll back down, don't worry. We want to grab it off of this curve. And I want to see that if we grab a point off of that curve, let's just say at x equals 0, okay, that our neural network will start to fit the neural network so it hits that point over time, okay? Gradient descent should say, hey, if there's a data point right there at 0.7 whatever, 0.77, right? Over time, that neural network should hit that 1 point, okay? If we keep training it on that piece of data, one data point. So 0, and so that is our, what do we call that? We called, oh, it's our original function we're trying to fit. What do we call it up here? Target function. There we go. So our data will be a target function, and we send in some input x, which is send in 0, okay? And just to make sure that it all kind of works, so I'm going to say, hey, just to make sure, I'm just going to test something out, make sure this all works fine. I'm going to say, hey, print target function, and I send in 0. Does that work? Hey, yeah, look, the value would be 0.76, roughly what we said, 0.676, 0.77. Great, awesome. So I'm going to get rid of that. So I'm going to say that our data is going to be equal to target function of 0. Okay. All right. Any questions so far? We are just taking we're taking forward propagation and back propagation and putting it all in a loop for gradient descent. Okay. And hopefully it only runs for a couple of loops, and every loop is going to print out what the weights are. Okay. Let's see if it goes crazy. And I'm going to run it all. Let's see what happens. Okay. It does not appear to have changed anything. That's not good. We don't want that. So it could be our, sure, I can go up to the forward propagation function, and maybe to save time, I'll also put it into the Zoom Slack, if that, the Zoom chat, if that helps. Is that okay? No, you got it. This is the forward propagation in the Zoom Slack. You can check out that chat. Where is our initial guess? It could be a function of our initial guess. In fact, I bet it might be. Where are our initial biases here? W list, -1, -2. So you'll notice that it's not changing at all. That's not good. That means our gradient is coming back zeros. That would be my guess, right? In fact, we can check. This is the value of doing debug steps. It's like, okay, why is this not changing? Either alpha is 0, which it shouldn't be. It's not 0. Or the gradient is 0. So let's check grad W1. W1. Rerun that. Okay. Yeah, grad W1 is 0 at all these steps. I don't think that's right. I think there's a mistake there. Okay. So let's take a look. So let's see, we got our back propagation step. That's where our gradient is being computed. So it could be in the gradient, or it could be in the forward propagation, our error, our problem, because it's sending in things that the gradient uses. It uses H1 and A1 and H2 and A2. We're doing some debugging, okay? So, all right, so if we're going through our computation of our loss. So our loss, we look at that. Oh, wait. Wait. It might be working. Friends. We're all friends here, right? I think we gave it the right answer. So it's giving us a gradient of 0 because it's perfect. Look, that's this thing we plotted here, this little dashed line over the black line. We picked, I believe, weights that are perfect as our initial guess. And if our value is perfect, my friends, if our weights and biases are perfect, what's the gradient going to be? 0. Huh. Interesting. Let's remember that. Let's change one of these weights here. Right now it's -1 and 2. Let's remember those, okay? In fact, we'll store it right here. It's at -1. So -1 and 2, I believe, are the correct answers. I'm putting it in the comments so we remember. And -4, 3. Okay? So that's the correct answers. Let me just change one of them to 1. Change the second value right there to 1. Now let's run everything all over again. And I guess before I do, I want to make sure I'm printing out the weights to see if things change. We'll keep printing out the gradients, see what happens. We're still getting 0 gradients. Maybe they're very, very small, but we'll see. Okay, let's change this so it prints out now the W list. List of weights. Do they change at all? It looks like they did change. Okay, they did change. It went from being 1, 1 to 1, 0, and it kind of converged there. So let's take a look at our gradient. And that could be, is that the right answer? It could be just fine. Let's see here. I guess the thing we need to do to check is what's the cost. If the cost is 0, then maybe we're in really good shape. So let's print out what the cost is. So if we're at the lowest possible cost, then maybe we're all set. Where's our cost function? It's called activation derivative, activation. Here we go. Loss function, predict data. Okay. Let's just remember that. What is our loss? In fact, let's compute that in the loop. Let's compute our loss. This is all in the gradient descent loop. Compute our loss, or our cost, whatever you want to call it. Our loss is equal to the loss function, and it's not y predict. We call it y hat. That's our prediction, right? Y hat. And let's print the loss. See what happens. We're debugging. This is how you debug maybe your code for your homework as well. Okay. Run that. Oh, look at that. Look at that number, friends. Is that cost low? Yes, it is. That's 10 to the -7th. Okay. So right now it's saying, hey, we're perfect. Okay. So that tells me that our guess is still close enough to that data point. So we got to kind of screw up our neural network. Excuse me, while we screw up our neural network more. We got to optimize it. We started off too good. Our initial guess here for our weights and biases, too good, too good. So let's just change it to, like, I don't know, 0.1, 0.1, 0.1, 0.1. Okay. That's our weights and biases. Okay, let's try running everything. And it's possible that, like, we still have an error. We're trying to debug it, right? Trying to debug where things are going wrong. Okay, I ran everything. We run all. Okay. Okay. Well, here we're seeing the target function here and where we want to go. And that's our actual neural network output right there. So you can see they're very, very different. So I would expect we want to be able to gradient descent that to make that, we want to optimize that so they're closer. But keep in mind, we are just trying to optimize the point. Let me zoom out a touch. We want the point there, these 2 points to line up right at x equals 0, because that's where we're grabbing that x value, that data point. Okay, now what happened when I ran everything? What happened? Oh, it seems like it's doing something. Look, my cost, this right now I'm printing off my loss or my cost. What's happening to my loss over time? Is anyone else getting something like this? What did I change it to? What did I change what to? The biases and weights? I changed all the biases to 0.1, 0.1, 0.1, 0.1, 0.1. Both biases and both weights. That's what I changed it to. Thanks, Chriskate, for the question. Look, my cost is going down. I am gradient descending, my friend. Interesting. Let me try to print out my weights over time to see if they are changing, or my bias. I think maybe my biases. Let's do the bias list, the B list. Because I bet at x equals 0, the biases might matter a lot. Okay, let's run it all over again. Okay. Sure enough, this here is my loss and the bias. Here's my loss. It's a little lower. And the bias is creeping up. It's changing the values of the biases. Look at that. Maybe my step size is too small for my gradient descent algorithm. Okay, let's try. Let's go up to the step size because it's very, very slow. Ticking up, like it's ticking down, it's kind of slow, right? So with that, let's change our step size. Instead of 0.01, let's try 0.1. You only live once. Okay. Let's run everything for good measure. Why not? Okay. Ooh, there's my loss. 0.4, 0.27, 0.18, 0.13. It's getting smaller, right? My loss is getting smaller over time. Great. We're descending the cost gradient. How about that? And we're ticking up, up, up. Look at those biases right there. They're actually changing pretty significantly. All right. And right now we're only doing 5 iterations. Who says we only have to do 5? We can just make it to be 10. And theoretically, we can just change it so it's a threshold. So it only stops when the gradient gets small enough. So let's compute the norm of the gradient. Compute the 2 norm of the gradient. Now you might recall the 2 norm, that's the distance formula, okay? That's just the square root of 1 squared, something plus the other squared plus something, okay? So let's compute the 2 norm of the gradient. So let's call it the grad norm, all right? And we don't need to take the square root, but so we'll just right now we'll just make it, and we will make it W list 0 squared, double asterisk is squared. And we want to do the same thing, which is W list 1 squared. These are all the elements of the gradient. Plus B list 1 squared. And then B list 1 squared. There are more mathematically elegant ways to write this out, but this is pretty much, this is writing it out explicitly for you all purposes, okay? And I can print out the gradient norm. See what's happening during the gradient descent step. Print out the grad norm. Yeah, I meant to put the gradient. Thank you very much for popping in my ear. Thank you. I apologize. I made a mistake. I wanted this to be the gradients, not the actual values. I would have made a mistake. Thank you, friends. So I'm just grabbing each of these gradients and not the actual values. My mistake. So it's the gradients of, and I don't even need these anymore, do I? I don't need these indexes, right? I don't need those. I'll paste this into the chat so you can all catch up a little faster. So just each of those 4 gradients squared and added together. Okay, we can take the square root of it, but that's not terribly important right now. Okay, so in the chat for folks. All right, let's see what happens to that gradient norm over time. Hopefully it's getting smaller. I'm printing out too many things though, so I'm going to comment out these other prints. I'm going to comment those out, So the only thing that I am printing out is the gradient norm, so I can track it a little better. Running everything. Hey, look at that gradient norm getting smaller, smaller, smaller. Okay. So here's what I'm going to do. I'm going to increase the number of iterations to start. And if I like what's happening, I might turn it into a while loop where I just wait for the gradient to get norm to get small enough to be beneath my threshold. Okay. So let's change this to, so let's try 20 iterations instead of 5 iterations and rerun it. Look at that. Look at that gradient norm. It's getting smaller, 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 right? Seems to be working. Now, outside of the loop, let's print out the weights and the biases that we get and see what happens. What's our weight list and what's our bias list? Okay. I'm not indented anymore. That means outside the loop. I'm outside the loop. I'm just printing out the biases and weights after the optimization. Right. Got to rerun this list. Okay. Well, look, it seems to be changing some of the weights and some of the biases pretty significantly. Okay. Let's try 50 iterations just to see what happens. It'll be fun. Iterations to be 50. Scroll, scroll, scroll. Look at that. 10 to the minus 6th. We're getting pretty small. Okay. And look, we're coming up with a set of weights and biases. These are our two weights. You notice it didn't care too much about this weight. And these are the biases, all right? Now, is that the correct answer? Well, let's find out. Up at the top, we had plotted this is our target function versus what our neural network produces when you have a whole bunch of inputs, right? Those are the two curves, okay? Let's plot that curve again after the optimization happens to see what happens to this black line. This is our neural network. What happens to it? So I'm going to go and I'm going to grab, so we need to make a loop. I want to do this exact same thing. I want to have this nice, beautiful plot, okay? I think we already have an X plot. We just need a new X hat plot, which is our prediction. And we can do that. Not a big deal. So what we're going to do is down at the bottom, I'm going to plot our target curve and our neural network curve. Okay, so in which point we already have an X plot. I believe we already defined that. So let's I think we have to do a loop. So we want to say we want to create we already have a y hat up higher, right? A y hat plot. We just want to update it here. So here's what we're going to do. We're just going to copy all this code here up to the for loop. Since we've already defined y hat plot of the right same size. Question. Copy all that. I'll put it down here. Okay. Now, we don't need all this stuff. This is forward propagation. We have a function for that. So what we're going to do is we're going to get rid of all of this stuff. Okay? And we're going to say y hat plot is equal to forward prop. And you have to give it, what are the inputs? You have to give it an x value. That's the x input. So that'll be x plot for the ith value of the loop. We're trying it for lots of different values. We're going to plot that curve, okay? Then we got to give it the weight list, which we have now updated. Weight list. And then the bias list. B list. Now, it does send back a lot more things than just this. We're going to try to ignore all the other things that forward prop sends back. Hopefully this will ignore it just fine. And then it will just plot that. Let's see what happens. Okay. Must be a string. We're in something up. We're close. We're actually extremely close. This is fun. To getting this thing to actually backpropagate and optimize. I think we're pretty close. All right, y hats. Not a tuple. Let's see. I think we might have to. Let's try putting in the, was it the H0, H1, H2, A1, A2? Not sure about that. Let's try it though. There you go. That did it. Haha! We're geniuses. You did have to make sure that you had all these other things that get sent back with forward prop, right? Okay. But look at these curves. Those curves aren't the same. Did we screw up? Let me send this into the chat for you all so you have it. Did we screw up? No. What data were we training our neural network on? It was on x equals 0. Where are our curves matching? Right at x equals 0. Hey, wait, does that mean, friends, does that mean that if I train it on other points on this curve, more of this curve will match up? Let's find out. Let's figure that out. Okay, so let's say we just changed it to, instead of being x equals 0 of our target function, it's x equals 1. We train it there. Does it work? Let's find out. So right now, target function at x equals 0. We're changing target function x equals 1. Let's run it. Then let's scroll down and see what will happen to our plot. It's getting closer. I'm not sure it's there yet. It might take a bit. Might have to, maybe we need more iterations. If we get more iterations, we'll get closer. Let's see. Right now we have 50 iterations. I don't like that right now we're plotting so many of these points. Let's get rid of that printout, okay? So I'm going to get rid of the printout of the gradient norm. I'm just going to comment it out, okay? And I'm going to change my iterations to 100. See what happens. And run everything. Did I do that wrong? The Y list, forward prop. Oh, I didn't change the input here. So this is the input. Right now here, this is 1. We set forward prop in with an input of 0. What we need is an input of 1. We change 1 to there. This is the same input. We'll call it our x. We'll call it our x data. Change it to 1. And we call this x data. That's what happened. This is our x data. Right there. Try all that again. Hey, look at that. Right at x equals 1, it matched up perfectly. So when we train this neural net on data points, therefore x equals 1, in fact, you know what? Here's what we'll do. Let's actually plot where that data point is that we're trying to hit, okay? Watch this. Let's show you plt.plot x data, y data. And make it a little, I don't know, a blue X, BX, and just run that. Boom. Look at that. Where I give it data, it's now lining up with gradient descent. Now let's give it more data points throughout more of this curve. See if we can get it to work. Is anyone getting this? We're training a neural network, friends, with backpropagation. Okay? So what we need to be able to do is, instead of having just training on one data point over and over again, let's train it on lots of different data points, one at a time. Boom, randomly selected along this curve. Okay? Stochastic, random gradient descent. Okay? So, or maybe just a bunch of different points. So let's make a list of points. Here's what we'll do. Got it. I know what I'm doing. We have 1,000 data points that were, sorry, the 1,000 loops. Okay, how many loops we're doing? Okay, all right. Nick, could you look up the modulo command for me real quick if you're listening? The modulo. I forget what modulo is in Python here. So we're going to create our x data instead of being one data point. I'm not sure we need that. We're going to make it a bunch of data points. We're going to make it np.linspace, just in between the numbers 0 and 1. Let's do 10 data points between 0 and 1. Okay? And target function, will this work if we just plug in the y data with the target with x data? Let's try it. Let's see if just so happens, it's going to throw an error, but I just want to see where it throws an error. Good. Okay. Awesome. Here's what we're going to do. Perfect. So we're going to run gradient descent. So let me just plot here y data. Perfect. That's exactly what I want. Awesome. So now we have not one data point at x equals 0 or x equals 1. We have 10 data points between 0 and 1. Okay? And y data is 10 data points between 0 and 1. We want to loop to do the gradient descent step on multiple data points. Okay? So we want to compute this gradient across all those data points. So we're going to want to do a loop within a loop here. Okay? So I'm going to create, so hopefully we finish this up today. I think we have just 10 minutes, just enough time. So it's like we want to loop and train off of multiple data points. Okay? So we're going to say for I is in range of 0 through the length of, what is it, x data. So for every data point, okay? All right, colon. Now, all of this is going to be inside of a loop, so we have to indent all this here. I'm sure there's smarter ways to indent everything. I am. Okay, and then the gradient norm, and then, no, I think that we're good here. Yes, here's what we're going to do. Awesome. Awesome. So all of this here is in the loop. This here is out of the loop. Okay? So this will loop the gradient and compute it. And if we change this to x data I and y data I, then it will compute the forward propagation and backward propagation for each of the 10 data points all in a row there. Okay? And it will store each of the gradients, okay, for each of those data points. Now we need to average the gradients for each of those data points, and then that is our gradient we use for gradient descent. Okay? How do we do that? Okay. So what we're going to do is we're going to create a running total of each of these gradients. So like when we have one gradient, we're going to add that gradient to 0, right? Then we have a second gradient, we add it to the previous total. Then we have a third gradient, we add to the previous total, and then when we're done, we divide it by the number of data points, okay? So let's at the beginning of this, let's call these, we'll call it GW1, that is the gradient of weight 1, it's going to start at 0. GW2, that's gradient of weight 2, it's going to start at 0. And then the gradient of the bias 1 is going to start at 0. And the gradient of the bias 2 is going to start at 0. Okay? Then after we've computed the gradient, we're going to add that gradient to our running total. These are our running total of gradients, so we can average across all data points. Okay? So therefore, we're so close, man. So GW1 is going to equal to the previous GW1, starts off at 0, plus this new gradient we just computed with backpropagation. Okay? Okay. Now we do the same thing we do with our biases and our other weights. So it'll be GW2 is equal to GW2 plus grad W2. So GB1 is equal to GB1 plus the grad of your bias 1. And then GB2 is equal to GB2 plus the gradient of B2, okay? And then these are the gradients that we use for gradient descent. So this is now going to be our running, we have to divide it, right? Once we're all done with the loop, we have to take the bias, this has to be out of this cannot be in that for loop for every step. This cannot be, I don't think. Now we're going to want to average it here. So what we're going to do, you can highlight all the lines. You highlight all the lines, hit tab. Sounds good. Okay, perfect. All right, so we need to say that GW1, to take the average. So GW1 is equal to GW1 divided by the length of your X data, number of data points, right? And the same thing for GW2 and GB1. GW2, GW2, GB1, GB1, GB2, B2, B2. All right. I ultimately didn't need the modulo, Nick. Thank you very much for the syntax here. Perils of switching languages between classes. Thank you. So, all right. So this is take our average to get the gradient across all data points. So now the gradient we use for the gradient descent step are these GW1s, these GW2s. So let's do that. GW1, GW1, excuse me. This is GW2. This is GB1. And this is GB2. All right, and then I have to change these gradient norms, but we're not using the gradient norms right yet, so we'll save that for later. Let's see if that runs at all. It ran. God knows what happened. And now let's rerun the plot. Okay. Okay. Not fitting everything just yet. Let's see if we can run more iterations, if it makes it any better. Let's make it 300 and let's run everything. Run all. Okay. It's kind of, is it shallowing out more? It's hard to tell. We're trying to make it fit all of those data points. The initial guess is pretty bad, to be clear, but it's kind of, but pretty, it's trying to span across all those things. Let's try a larger step size. A larger step size. Let's try 0.5. See what happens. Run everything. After I change the step size to 0.5. 0.5 step size. That's shallowing out more? It might be. It might be. Let's do 1,000 iterations. I think it is. It's just taking a long time. I think we need a larger step size. Let's try a step size of 1 or, oh my goodness, 2. Oh, there we go, my friends. I changed my step size to 2. I'm running 1,000 iterations. It's a lot of iterations. Okay? But look, for those data points, it's fitting the curve. How about that? And I had picked data points between 0 and 1, and it's fitting the curve. We're fitting the neural network to the data that we're giving it. Let's try widening the data. Let's have it over. Let's see, can we get more of that curve? Can we go from maybe -2 to 2? I'm curious. Let's see if this will work. So right now we are gathering data between 0 and 1. This is X data. Let's go from -2 to 2. And let's do some more data points. Let's do 50 data points. Okay? And run everything. See what happens. Might take a little longer. Okay. It's starting to fit more of it. It's not hitting that curve just right yet, right? Not quite hitting that curve. Let's see if we can change that a little bit. See, these are our biases and weights, by the way, that are coming out. Let's see. How do we get that to fit better? Where are we? Oh, I think it might be helpful now to compute our gradient norm. So let me grab GW1, replace this with GW2. This is GB1, and then GB2. I'm just going to print this gradient norm once the entire optimization is over. So I'm going to print grad norm and see what it looks like. Oh, it's very, very small. It thinks it's very, very close. Okay. So we're going to do some other things to get that working right. Well, let's see if we can change anything else before we finish today. But we can clearly see it's learning, right? We are making this neural network learn that curve by exposing it to those data points over and over and over again, computing the gradient via backpropagation, and then gradient descent. Okay? Question? Yes, you can take the square root of it technically, and that'll make it much closer to further away from 0. Yes. Yes, you can. You absolutely can. No, because we're not even using it right now. We're not even so we're not taking the square root right now. It's np.square root. Right? Yeah. There you go. It's much less small, right? Because we take the square root. But yeah, we're not using it right now. We're just looking at it. And it's quite small. So it's clearly hitting the bottom. No, great question. So let's see if we can let's look at other data points along the curve. Let's go for, where am I setting my data? Excuse me, I apologize. I'm trying to find my data. Where's my data? Set my data here. Here we go. It's like this. We're selecting our X data. We're almost, we have a functioning backpropagation, guys. This is cool. This is all for bonus. This is me just having fun trying to fit these curves, okay? So, and you can have fun too. See if you can get it to fit the curve. So let's see if we can do from -2 to 0. Can we fit that curve? That's more the steep part of that cool curve. Let's run everything, and let's do fewer points. Let's see 20 points. Okay? It's -2, 0, and 20 points. Well, it's trying to hit. It's doing a very flat line though. So maybe it's possible that maybe my step size is too big and it's going towards 0. Let's go 0.5 again. Run all. Step size 0.5. Not working great. Let's make it smaller. 0.1. Kind of. Too many loops, too many iterations. What happens with 10 iterations? Does it get anywhere close? Nowhere close. So 100 iterations. I'm just playing around with the step size and iterations to see how it works. Do it for yourself. See what you come up with. Okay? So with that, we'll stop for today. We might have to normalize some data, is my guess. We're going to have to start normalizing things is in order to get this to work better. But that's the structure of backpropagation. We did it. We did it. And there are even smarter ways to do it. Okay? So with that, thank you so much. I'll stick around for questions for a little bit.